Thank you, Nate, for the introduction. So today I'm going to talk about randomized algorithms for estimating logarithm-based quantities. There are two joint works with my advisor, Dr. Drineas, and some other collaborators of ours. And more specifically, I will talk about two quantities. The one is the log determinant of a symmetric positive definite matrix that is usually appearing in applications like optimization or machine learning. And the second one is the entropy of a density matrix, the von Neumann entropy of a density matrix, which is very, very important in the field of information theory. So I will begin the talk with the log determinant, which is formally can be said that given a symmetric positive definite matrix A, we want to estimate or ideally exactly compute the logarithm of the determinant of this matrix. So why we want the matrix to be symmetric positive definite is because the eigenvalues will be greater than 0. They are all positive. So we don't have any problems to compute the logarithm because there is no logarithms of negative numbers or 0. So let's think about this problem. Yeah.
So this is also the log of the product of the eigenvalues?
The log?
The product of the eigenvalues too.
What do you mean? Like, yeah.
Okay, sure.
Yeah, because the determinant is the. I will talk about this.
Okay.
Like, yeah. Okay, let's think the problem. A very naive way to solve this problem is to first compute the determinant of A and then compute the logarithm. Okay, this is a very straightforward computation, which is not easy because computing the determinant is not easy. Another more sophisticated way is that we all learn this way in linear algebra courses, is to compute a decomposition of the matrix, let's say the LU decomposition, and then manipulate with simple algebra the log det and derive the proper formula for computing the log determinant. So here, because our matrix is symmetric positive definite, we can use the Cholesky decomposition, and our log determinant will be equal to 2 times the logarithm of the product of the diagonal entries of the Cholesky factor. But although the Cholesky decomposition is cheaper than the LU, it's again running asymptotically in cubic time. So it is easy to understand that if we go in higher dimensions, our algorithm will not scale. And also another problem of these direct decompositions are that they use the entire RAM usually. We have to go in block methods to tackle this problem. So we don't like using all this memory when we are computing these quantities. Yeah.
So are you assuming that A is dense or sparse?
We are assuming like a dense matrix. We don't explicitly say that our matrix is sparse, so it's a more general. Yeah, I don't talk about special cases like sparse matrices, or like these methods are applicable to any matrix.
But I guess just the matrix is dense. You've got to store it, so you don't even want to store the matrix in memory.
Yeah, exactly. So we don't want to do the Cholesky decomposition or the LU decomposition, or
but you don't even want to store the matrix.
Yeah. So we need the matrix in the RAM usually to like compute this. Like, okay, if I go in supercomputing techniques, I don't need the entire matrix in the memory. But if like I'm talking about the regular, like a regular computer. I'm not talking about a supercomputer or something. We don't like want to bring the matrix in RAM and then run the Cholesky decomposition, because this will like stress our memory, because we have to store the matrix and also the Cholesky factor and all this stuff. There are other ways to tackle problems, but we don't consider them over here. So yeah, we have the cubic complexity that we don't like. So let's think like how we are going to tackle this problem from our perspective, like using randomized algorithms. So we are going to derive a randomized algorithm where first we manipulate the log determinant mathematically, and then we use random LA techniques and results in order to achieve a satisfied quality of approximation. Satisfying quality of approximation. Okay. So because our matrix is symmetric positive definite, it is always diagonalizable. Okay. So I can I can write this eigenvalue decomposition over here, where lambda is this diagonal matrix of the eigenvalues, and U are the eigenvectors of A. And because A is symmetric, all the eigenvectors are orthogonal, so pairwise orthogonal. So we have here the U transpose. Okay, and from the definition of the like matrix functions, we know that any function we apply over here, we can apply it on this matrix over here, like the eigenvalue matrix. So actually this one will be det U, det lambda, det U transpose. So that U and U transpose will be the same, plus minus 1, because these are orthogonal matrices. And because we have that U square, it's always positive. So this thing over here will be that of lambda, and then the log. And this will be log of the product of the eigenvalues that you said over here. And the properties of logarithm, this is the summation of the log of lambda I, and this is the definition of the logarithm of A. Like, let me, I don't think I have read. So the logarithm of A, if we have the eigenvalue decomposition, will be so this quantity over here is the trace of this matrix. Yes?
So log of the diagonal matrix is in the log of every entry on the diagonal?
Yeah.
Okay.
Okay, so we have gone from here to this expression. So the log det is equal to the trace of the log of A. And we have two things over here, okay? To compute the trace is very easy. But this needs to have the logarithm of A, which is again, the time is cubically because of this one. We don't know how else to compute this one. So we further go and manipulate the trace of the log of A. So we use a lemma that is a generalization of a series that is produced from the Taylor series, which says that if I have a symmetric matrix A with eigenvalues that are lying in the interval -1, 1, then I can approximate, like I can compute this function over here as the infinite sum of ak divided by k. So I'm going back in this formula over here, and I plug in this thing as follows. So I say that the trace of the log of a is equal to the trace of the log in minus in, I can like do this, plus a. Then I form trace log in minus this matrix over here that I denote as c, and this becomes trace of log in minus c. And then I plug this formula over here and like over to estimate this one, and it becomes trace minus the summation from k equals 1 to infinity of ck over k. And because the trace of a sum is the trace of its particular summand, I can do this one. Like I can say that the trace of log of a is minus the sum from k equals 1 to infinity of the trace of ck over k. So we have again two major concerns over here. The first one is how I compute an infinity sum. This is very simple, like I truncate a Taylor series. And how I compute this trace over here, I don't want to compute c in the power of k. So here we are using randomized trace estimators. So let me give you a definition about the trace estimator we are using. It's from a work of Vron and Toledo, the results that we are using. So this is the simplest trace estimator that someone can, the simplest randomized trace estimator that someone can have. And it's the Gaussian trace estimator. And what I do is that I create random Gaussian vectors that I denote them as gi, and then the trace will be 1 over p sigma from I equals 1 to p gi, sorry, this is the Gaussian estimator. 1 over p, the sum of I equals 1 over p, gi transpose a, gi. Okay. And from this work over here of Vron and Toledo, we have this result that the trace of a minus g is less or equal to, like we have a relative error approximation, like I get an approximation of epsilon, of relative error epsilon. Okay, yeah. So this gives us, all this gives us a simple algorithm that says that given a matrix A with eigenvalues that lie in the interval theta 1, 1, and a parameter, accuracy parameter epsilon, and the number of Taylor terms that I keep, and I denote as m. I first compute the matrix C, which is the identity minus the matrix A, and then I create the random Gaussian vectors, which this lemma over here should be this much to have the relative error approximation, and then I compute the log determinant of A as the summation from k equals 1 to m, 1 over p, sum of I equal 1 to p, gi transpose ck, gi. Okay. And of course, we compute this like we don't compute it like we don't go into the c in the power of k. Okay, we do this one. We do the matrix vectors. Okay.
And how do you get hammer? We're going to talk about that.
Here is a lemma that we derived that says how to what should be m in order to have, like, this is the lemma of the, like, the main theorem of the of this algorithm that says that I can, if I have the matrix A and the accuracy parameter epsilon, then we can prove that with a probability at least 1 minus delta, I can have a relative error approximation that is 2 times the accuracy parameter epsilon. And to derive this one, I have to have m to be greater than this this quantity over here.
And what is sigma 1?
Sigma 1, it's theta 1 is the lower, like the bound of the eigenvalues. Where is it? Here? It's the lower bound of the eigenvalues.
There it is. Okay.
Yeah. Yep. Oh.
No, just thinking about it.
So.
Sorry. Oh. The eigenvalues lie in theta 1 to 1?
Mm-hmm.
Okay.
Okay. And this is the running time we get, which is less than yeah.
Your value is p. I know you gave a bound on it. P is like your number of samples. Is
Yeah.
right?
Like the number of Gaussian vectors I get.
Yeah. How does p compare to the size of the matrix? Not related.
So. From all the experiments, actually I don't have experiments on this, the relative error approximation, because when I go, these algorithms are good when you go in large data. So if my eigenvalues lie in the interval 0, 1, then I have the problem that when I go in large matrices, I cannot compute the real determinant of them, because there are numerical errors that are happening over there. So the determinant I get back there, it's not that, like, it's not right. Okay. But in other experiments that I did, for example, in the entropy, that I'm going to talk about this later, you can use like a few Gaussian vectors in terms of n. Like if I have a 5,000 by 5,000, I can use matrix 5,000 by 5,000. I can use p equal to 10 or 50, like, to get a very good approximation. So the problem is mostly on the truncation of the Taylor series and not on how many Gaussian vectors I'm going to use. So these are the, so there is a difference between theory and experiments. So the theory gives us this number, but it's not necessarily what we use in the experiments to, like, get the results we get. So usually p and m are user-defined variables when you do the experiment. I don't know if I answered your question. Okay. So yeah.
Just one random question out of pure curiosity. So you're using the same vectors p for each of the different terms, right? In your Taylor series.
Mm-hmm.
You could use different vectors p.
Yeah.
Is there any reason that you would? I mean, I can make arguments either way. Certainly, from a random number perspective, it's better to have fewer random.
Yeah, we haven't, like, tested it, but it's a good idea. Like, yeah.
No, it could very well be a terrible idea.
Yeah, I don't know. We haven't checked this, so I don't know if it will be much difference, because, as I said, like, the problem is on the truncation of the Taylor series and not that much on the Gaussian vectors. What Gaussian vectors I get, or, like, I don't know if I will get a better result.
Yeah.
But it's a good
multiple
idea.
Interacting things here.
Yeah.
Right? Because,
Yeah, it's a good idea.
I mean, like in some sense, you're not like you're somehow using your randomness twice, and so you've got these results with high probability,
Mhm.
but you're using the same random numbers for your next estimate as well.
Mhm.
And so I don't know if that matters or not, but
Yeah. Yeah, I don't know. Okay. Any other question on the log determinant? No? Okay. So I will move on the next quantity, the von Neumann entropy of density matrices.
sorry.
Yeah.
I guess I'll do a few more questions, which
Okay.
may be exactly this. It's not about the algorithm, it's about what.
Okay.
Why you want this?
Why?
Yeah.
Why we want to use this algorithm?
No. What do you do with the numbers that come out?
From what?
The log determinant algorithm.
So I don't like. It's something that is used. So for example, in interior point methods, the log determinant is used as a barrier. So I don't do something specifically with them. I just give the algorithm to compute this quantity.
Okay.
If this is what you mean, like anyone can use this if they want to approximate this and they have problems approximating this because of the small eigenvalues. They can use this and like tackle their problem. Other question? Yes.
So in the trace estimator you just gave us, the sampling amount P was proportional to 1 by epsilon squared. Are there other ones that are better than that, like maybe log in 1 by epsilon squared, something like that?
Like we have, like you mean another trace estimator?
Yeah, that's
Like we have talked about this in, we have talked about this in the class in RandNLA that there are other trace estimators. I don't remember their bounds now, like
Okay.
to talk about this, but there are other trace estimators. This is the easiest one.
Okay.
Like there are more sophisticated trace estimators that are using Hadamard transforms or like transforms like this, but they are very difficult to be computed fast.
Okay.
Like with what we have, like we cannot do it fast in MATLAB, for example. Yeah, they need other supercomputing techniques and stuff. Yeah.
So one other question is, another approach to estimating this would just be to estimate some of the extremal eigenvalues of the matrix A and just compute the result on that subset of eigenvalues.
Okay. Yeah.
Do you, I mean, the downside there is the complexity of that operation is really hard to state because it depends on.
You mean like a random projection, like project
Not
and.
random projection is run AR pack on your matrix to get the smallest 100 eigenvalues or something like that.
Okay. Will this like help, like again if you have like very small eigenvalues?
So if you have, it turns out that runtime is more proportional to if you have any gap anywhere in your spectrum.
No, it's not only the running time. Like it's also the computation. When your eigenvalues are in 0, 1, and your matrix is large, then if your first 100 eigenvalues are really small, then aren't they going to be errors, numerical errors when you compute this? Like your product is going to be 0 or like none or something like that.
You compute the eigenvalues and then take their log and the sum of the logs, right?
Yeah.
So, fine, your eigenvalue, like you don't, this isn't necessarily going to be a high accuracy algorithm. It's not going to be 16 digits.
Yeah, I mean you can do this.
Okay.
We're just we like randomized stuff. So
I just want to know which one's faster.
yeah. To be honest, I have. To be honest, I haven't checked this. We do randomized algorithms, so we.
But I want randomized things that are faster, right?
Yeah, it's like, yeah.
Eugenia, I have a quick question too.
Yeah.
You said all these results are for eigenvalues between theta 1 and 1. Remind me quick how you generalize things for like A that has larger eigenvalues.
Yeah, so essentially here, the way we get the log determinant, there should be another factor over here. If I don't know if you remember, it's a log of the bound of the largest eigenvalue inverse.
Okay.
Actually the approximation of the large eigenvalue inverse, and it's if I remember, it's plus this one, but we get a relative error approximation and not an additive error. Sorry, I would get an additive error approximation, not a relative error approximation. Okay. In this, like when you generalize, it's exactly the same, but because we want to use this Taylor. Actually, I will show a similar technique on the entropy if you want. We can talk about this later. So, other question? Yeah.
Quick question. I know you said essentially you have P and M, you have a theoretical bound on them, but you pick different numbers when you're running experiments. So one question is, first of all, do you still have to find the smallest eigenvalue?
For this one, no, because I bound the eigenvalue equal to 1. I say that the smallest eigenvalue is, sorry, the largest eigenvalue is 1.
But didn't you say your eigenvalues are between theta 1 and 1?
Yeah, but I don't use the lower bound.
So you don't use the lower bounds at all in your experiment?
No.
You don't even pick a number that is bigger than those bounds?
You can do this, but you just put random numbers, like you say, excuse me.
You did have a 1 over theta 1.
Yeah, we have it.
Complexity, right?
Yeah, m should be greater than 1 over theta 1, 1 over theta 1, log 1 over epsilon. Yeah.
Sorry.
So the thing is, this is the how m works. Okay, to derive the relative error approximation, but when I do the experiments, I just put numbers that I like, and just I don't run for this, because these quantities can get very large, and there is no reason to run my experiments for these large quantities when I can get a good relative error by using smaller quantities for m. This, I don't know.
And how can you estimate the relative error if you don't have the right bound?
How estimate? I get I compute the real entropy, and then I compute the real log determinant, and then that's why I'm saying it's I cannot test this algorithm. I haven't tested it yet because I cannot get a real log determinant for this. For large data, I can get for small data, but not for large. If I go to 30,000 by 30,000, I don't know how to compute the determinant of this matrix.
But you just need the Cholesky factor, right?
Yeah, but then if I take the product of the diagonal entries, it will not be.
But it's the log of the diagonal entries, isn't it? Or do you need the product?
The log of the product.
Yeah, so take the log and then take the sum.
Yeah, we can do this. I don't, to be honest, I don't remember why it wasn't working right now. I have to check this. Okay. Yeah.
Sorry, one more random question here that you'll indulge me in. Do you know the conditioning of log determinant?
Conditioning?
Yeah.
Do what? Stability and stuff? What?
Yeah, can you just work out the condition for the log
No.
function?
No. Okay. No. Okay. So if there are no other questions on the log determinant, I will move to the von Neumann entropy of density matrices. So what is the density matrix first? So density matrix is a matrix that all its eigenvalues are probabilities and they sum to 1, so its trace is 1. And the eigenvectors are representing usually statistical mixture of pure states in quantum mechanics. So it can be written as this form over here, and the matrix, where with capital C I denote the orthogonal eigenvectors, and sigma p is the diagonal matrix of the probabilities of each state, which are the eigenvalues also of this matrix. And this trace is of course 1 because these are probabilities. And it is like one of the most important quantities in information theory, the log determinant. So again, actually the not the log determinant, the von Neumann entropy. Okay, we compute the von Neumann entropy. This is its formula. It's minus the sum from I equals 1 to n of sigma I log sigma I, where sigma I are the eigenvalues. And again, to do this, as we saw previously on the log determinant, there are usually cubic time algorithms, the direct way, okay, to do this, not the. So again, this is prohibitive for large data, so we have to do something different. And again, we manipulate the von Neumann entropy of this of the matrix. So first, we will assume a function hx that is x log x, and I plug into this function the matrix R. So I have hr equals R log R. And then if I have the singular value decomposition of this, it would have been psi sigma p psi transpose log of the singular value decomposition again. And as I said over here with the definition of log, I plug the log on the sigma p. So this would be psi sigma p psi transpose psi log sigma p psi transpose. So the psi transpose psi, they become identity. So the quantity will be psi sigma p log sigma p psi transpose, or psi. I don't know how you just say. Yeah, you understand that this one over here is the h of sigma p, right? Or do you want me to explain why this one is that one? Okay. Oh, okay. So then I go, like, I want to manipulate h of r. So I said that h of r is the von Neumann entropy, and it's denoted like this. Here I just use pi instead of sigma I, because I said that the probabilities, the eigenvalues are the probabilities, so I say pi. And this is actually minus the trace of h sigma p. Is it clear, this one? Okay. Then, because the trace is a nice function, let's say, and operator actually, and we can do stuff over here, we just put psi transpose over here, which is the identity, and I can do the circular, like with a trace, I can circulate the things inside here. So this becomes minus the trace of this eigenvalue, this singular value decomposition of h sigma p, and this becomes, because I said that this one is equal to this one, so this becomes minus the trace of hr. So essentially, I found that the entropy of R is equal to minus the trace of this one. Okay. This is what I want to see, like to find. So we consider two approaches. The first one is again using the algorithm we used for the log determinant, like truncating the Taylor series and using the trace estimators. And also, instead of truncating the Taylor series, to estimate HR using a summation of Chebyshev polynomials. Okay. So when I use the Taylor series, so this is Nate, what you were asking. Like this is how we derive. Like I can show it right now. Okay, so I have this one, which is equal to HR equals minus the trace of R log R, because I said that h of x equals x log x. Okay. Then, because I want to use the series that I said that log of I minus a equals the sum from k equals 1 to infinity of a k over k, but this matrix should have eigenvalues in I will say, so in the real, in the general thing is like it should be minus 1, 1, but here because we have probabilities, we will say 0, 1, okay? So we want our eigenvalues to be in 0, 1. So I'm going over here and say that this is R log, where U is the estimation of lambda max. Okay. And then I'm doing log U trace of R log U plus minus the trace of R. Okay, up to now. And this is actually minus log U trace of R. The trace of R is 1. Okay. Minus the trace of R log U inverse R. So I have minus log U here, and then this one becomes the trace of R log time minus the trace of R I will denote this as C, so I will have minus log U minus the trace of R log in minus c. And actually this, if I plug the this one over here, it would be minus the trace of r sigma k equals 1 to infinity of c in the power of k over k, where c is the identity minus u inverse r. And then here I truncate the series. Here I take some of them, and I also use the trace estimator. Okay, we have log u. Sorry. Any question on this? It's simple algebra. Okay. So this is also how we derive, in the general case, the log determinant formula. Okay. So the algorithm again is simple. We compute the approximation to the first, the dominant eigenvalue, and from because we are using power method to do this one, there is a result that bounds the dominant eigenvalue. So from this result, we have to get the minimum between 1 and 6 times P1, which is the approximation to the dominant eigenvalue. And then we we compute C, which is the identity minus the approximation to the eigenvalue, the dominant eigenvalue times R. And again, we use these match probability vectors, sorry, Gaussian vectors, and we compute the log determinant using this this formula.
Why do you have to do P1 hat and not
Two?
P1 hat?
Because I want to get, so actually my eigenvalues are 0, 1, okay? But they can, because they are probabilities, they might be like their mass would be like concentrated in some area. So by using this one, the U inverse, which is the approximation to the dominant eigenvalue, I normalize the spectrum. I take it between 0 and 1. Like the dominant eigenvalue will be.
Estimation of the,
Excuse me?
why do you need an estimation for the dominant eigenvalue?
Because I have to do because I have to do this approximation over here with the Taylor.
You can get the actual eigenvalue, that's what I'm saying. You can get.
Again, it's an approximation. You can use eggs, but eggs again is like I use eggs. Okay, I don't run power method. I use the eggs of MATLAB, but the eggs again is an approximation to the dominant eigenvalue. It's not like it. You can get the actual eigenvalue with very good error, but like it's again an approximation. Okay. And then we derive our theorem, which says that if I have R with probability, which is the density matrix, with probabilities Pi, then I will use algorithm 2 to derive the, to find the von Neumann entropy, and with probability at least 1 minus delta, I will have an approximation that is that has a relative error of 2 times the accuracy parameter. And again, I derive a value for m, and the computation time is this ugly thing, which is again less than n cube in most circumstances. Okay. So now I will show you how we use the Chebyshev polynomials. So we, from the Chebyshev polynomial theory, we know that we can approximate h of x, which is x log x, I remind you, in the interval 0, u, where u is the dominant eigenvalue, by using a convolution, I would say, of Chebyshev polynomials of the first kind that are of this form, and with coefficients alpha t that are derived by these formulas over here. Okay. And then there are some results on the approximation of h of x by this convolution of Chebyshev polynomials that says that the absolute error would be less than the approximation of the dominant eigenvalue divided by 2 times the number of Chebyshev polynomials I use square. Okay. And my problem will be now that the entropy will be estimated by the minus the trace. If you remember, it was minus the trace of HR, and because I approximate HR by FMR, I will plug FMR over here, so it would be, now I have only to approximate the trace, so it will be minus 1 over p, sigma I equals 1 to p, the number of Gaussian vectors, and gi FMR, g, here I forgot the transpose, okay, and here. So we again use the Gaussian trace estimator, and to compute the Chebyshev polynomials, we use a very well-known algorithm. It's the Clenshaw algorithm that is used to compute Chebyshev polynomials. It's a recursive algorithm. I will not get into this. So the algorithm again is very simple. We have the same dependencies as in the previous algorithm, but the only thing that changes is the formula over here. Okay. And to compute this one, I again said that we use the Clenshaw algorithm. Any question? Yeah.
Where does this magic number 6 come from in step 2?
So there is there is a handout by Luca Trevisan. I think I talked briefly about this when I was presenting the log determinant, where there is a derivation about bounding the dominant eigenvalue when you use power method. So it comes from this one. Okay. Any other question? This is our theorem. Now our approximation gets a relative error of 3 times the accuracy parameter, and this is how many Chebyshev polynomials we have to use, and the computational time we derive. I don't like this these huge things. Okay. Any questions on this? The Chebyshev and the Taylor? Yeah.
Where, curiosity, does the 2.5 over the epsilon come in?
Oh.
It's very particular.
I think it's like so. If I remember correct, I'm not sure, but because you have to take the it's something like there was a square over there, okay, and it's 1 over 2. So somehow there is another u that plugs inside and becomes 2.5. I don't remember exactly.
So intuitively, this giant square root thing, how does this grow and what traits of R?
Excuse me? Say it.
So I have essentially no intuition of how I can look at this square root here and go, if R is big, this value is big, or is this based on sparsity in some way, or how does this factor grow?
Which vector?
The factor root u over L log 1 by 1 minus L. Is it
like u is the dominant eigenvalue, okay, and
I and L is what again?
L is the, L is the smallest eigenvalue. Okay, if you see over here, 0 is like, this is the lower bound of L, and, of pi. So, I never like checked on this, how this like goes.
So if it's between 0 and 1, this is actually a small term. No, not necessarily.
Yeah, it depends on like, you have to compute this one and
In
check.
some ways, are like conditioning of the matrix almost. It's like the properties of the matrix will change how good or bad this term is.
I'm not sure. Okay, any other question? No? Okay, so this is a future work that I am going to present. And it's one of the cases that are very interesting. And it has to do when our density matrix is low rank, which means that only some, let's say k, at most k, of its pure states are linearly independent. So this means that at most k of its probabilities are greater than 0. Okay, they are positive. And n minus k probabilities are 0. And this means that the Chebyshev and Taylor approaches are not working, so we have to do something else. And this is to, we thought of using random projections. This includes how we are going to fastly construct a random projector. So there are many cases that we considered. The easiest one is the Gaussian random projector, where we just derive a matrix, a Gaussian matrix of size n by s, where s is very small in terms of n, okay, which is the size of the matrix. There are the subsample randomized Hadamard transform, which has like the nicest properties, but actually we cannot use this in matrices that are not powers of 2, its size. Actually we can use it, but we have to pad with zeros if we want to do this, and this doesn't add something. And also, I'm not sure there is a technique in MATLAB, for example, an easy technique to fastly compute subsample randomized Hadamard transform. And then there is another transform, the input sparsity, which is very good when our matrix is sparse. And one that I'm looking right now, it's the Hartley transform, that are actually, there are some algorithms that compute this transform fast. So this is an algorithm we are using. So first, we are given the density matrix R and the low rank density matrix R, and an integer parameter k, which is the number of, actually the rank of the matrix. And we want to approximate the von Neumann entropy. So we first construct the projector, the random projector, with one of these techniques. And then we multiply, like we project our matrix in that space and do a simple SVD because this space is very small, and just compute the von Neumann entropy using the, actually there is a minus over here that again I missed, using this quantity, which is the proper formula for the von Neumann entropy. Okay. And now we get an additive relative approximation theorem. actually we can, using this algorithm, okay, and ensuring that with probability 0.9, we ensure that the squares of our probabilities are the relative, I don't know how this is called, like the square relative error of the ith probability is less than the accuracy parameter. I get this error over here, which is relative because of this one, the square epsilon factor, and additive because we have this factor over here, the square 3/2. And if we use the input sparsity transform, we can get a running time of proportional to the non-zero entries of the density matrix plus n times the rank of the matrix over epsilon in the power of 4. Okay. I just present this result because this is the best running time we can get. Okay, any questions? I think this is the simplest algorithm. Like, so I will show you some experiments on these algorithms for the von Neumann, for the approximation of the von Neumann entropy. And all these experiments run in the Snyder cluster. I don't remember the specification of Snyder right now. But it's a fast computer, I know. It's a fast cluster, actually. So first, we used the 5,000 by 5,000 random density matrix. And so I remind you that M is the number of Taylor or Chebyshev terms that we keep. P is the number of the Gaussian vectors we use, and U is the approximation to the first to the dominant eigenvalue. And here we use the dominant eigenvalue to be lambda max. So we checked different values of the eigenvalue, the dominant eigenvalue, like we took 3 times the lambda max or 6 times the lambda max. But the best results, we got them for for U equals to lambda max. And because it's, as Huda said, it's very easy to compute to approximate the dominant eigenvalue. So for example, for this experiment took less than 1 second using eggs. We used U equals lambda max. And as we see over here, our relative error is always for the for both methods less than 1% actually. The no trace estimation over here, actually the NTE is the no trace estimation algorithm that serves as a bound for the results we get when we use trace estimator. Okay. You cannot see it very well over here because the plots are really, so the results are overlapping the one the other, but it's a little bit obvious over here that the no trace estimation is always under all the other curves. So in terms of time, of course the no trace estimation algorithm took a long time because actually we compute the trace explicitly, like we do the matrix multiplication and then like the powers, okay, and then we take the trace of this, so it took a long time. But then for the rest of the piece, like the other algorithms with the trace estimation, and as you can see here, for P equals 50, I have a result in 2 seconds for the Taylor and in less than 3 seconds for the Chebyshev. while the exact computation using the SVD took 1.5 minutes. Okay, and I just computed the singular values, not the singular vectors. Okay. So actually, we can get a very good result only by using this number of Gaussian vectors. This is I think this is for m equals 5. So for m equals 5 over here, where I have very good approximation, less than 1% in both things, and use 50 Gaussian vectors, I get a result that is really good. Okay, 1% relative error in like let's say 3 seconds max, while the exact computation took 1.5 minutes. Okay. And then we went to higher dimensions. So this is the highest one that I could load into the memory in Snyder. It's a 30,000 by 30,000, and actually perform computations, because I could load a larger size of matrix, but I couldn't perform computation in this. And the M was the number of Taylor and Chebyshev terms was varying from 5 to 20 with steps of 5. And again, U was approximated as lambda max. And here again, I managed to get results that are less than 1% in all cases. And here I present the time results, where I always got results back in less than an hour, and the exact computation took 5.6 hours. And I also have like a very good approximation over here on the other. Yeah.
What is the benchmark for the exact computation?
What is?
What did you use?
Running the SVD only by using only computing the singular values. Like you can in MATLAB you can do.
But you don't want to do that.
Yeah.
S is equal to SVD of A, it runs a different algorithm.
What?
If you just run S is equal to SVD of A, it runs a different algorithm.
Yeah, this is not what I ran this one.
Which one?
Like this one.
Yeah, so that actually computes U of V.
Yeah, but I think when you run S equals SVD of A, it's not returning all the singular values.
It does. Well, at least when I used to use MATLAB.
Okay.
It's like the QR factorization, but also not.
I just used this one.
Okay.
The other thing is if the matrix is symmetric positive definite, isn't it better to use isn't Chomsky factorization faster?
But these aren't SVD, are they?
They are.
They are?
Yeah.
Okay. Then you should definitely use probably.
I didn't want to use I just wanted to perform the exact computation as compute the singular values as we know we compute the singular values, and then go and do the rest.
Wait, sorry, so this is to do the matrix, or so the Neumann entropy or the log? Yeah.
This is the von Neumann entropy, which is pi minus pi log pi, and summation
So
of
you
this.
can't get that one with the Chomsky factorization.
Yeah, I mean,
But if you're, but
how let me think. How you get the eigenvalues by the Cholesky factorization?
No. This was the algorithm on the first one.
Oh yeah. Oh okay. Yeah. You don't have a determinant over here. Okay. That's why I was like, I don't know. Maybe there is something I don't know. Okay. And actually, the approximation of the lambda max equals 3.6 minutes. with eggs. So this is the third experiment, which is with random projections, and here we have, because I wanted to test the Hadamard transform, I took a matrix of 4096 size, and as you can see over here, for rank equals 10, 50, 100, and 300, all our methods performed, like all the transforms performed almost the same, and they resulted in like always less than 1% relative error, actually less than 0.5% relative error. And here I present the results for the time for the same ranks and different, I think. Now, S is the number of, it's actually the number of columns of the random projector. So here you see like with few elements I can get, for example, for k equals 10, I can get in less than 1 second an approximation that is between 0.1% and 0.2%. And the same is happening with this one, while when I computed the exact computation, again using SVDS over here, I got the results in 1.5 seconds for the rank K, in 8 seconds for rank 50, in 15 seconds in rank 100, and 1 minute in rank 300. And here, as we can see, everything is like less than 2 seconds. Okay, we are way faster than SVD. And then I went in larger dimensions, 16,000, about 16,000, to again test the Hadamard transform. And we managed to get, again, very good results. Actually, as we see over here, as the rank goes higher, I get a worse approximation error. This is something I want to test why. The time is again very good. Here is in seconds and here is in minutes. And the exact computation for rank 50 was 1.6 minutes, while I have at most 40 seconds over here. And for the rank 500 was 20 minutes, while I have up to like 1.5 minutes over here. And this was the, I don't know, do you have any questions on this? This is the last slide of my talk. Yeah.
So from the theory perspective, can you describe in a somewhat intuitive trade-off between the truncated Taylor series and the Chebyshev polynomial methods?
So usually the Chebyshev polynomials give a better result in approximating algorithms than the Taylor series,
yeah, but in this
like approximating functions, sorry. So as you, like, this is not the, like here you see, it's always performing better than it's almost always, because there are some areas that I still don't understand why this is happening. I guess it's something to do with computational errors that are happening. And the Chebyshev is always approximating better than the Taylor.
Okay, so, and from the theory side, is this the same? Does the theory say that Chebyshev seems to be performing uniquely better than the Taylor? Or is there a trade-off?
Usually, from the application side, no. Usually the Chebyshev polynomials are approximating better than using the Taylor, because the Taylor is more like general, I would say, and the Chebyshev is working like, if I remember correct, for the Chebyshev, it concentrates right here and then goes right something like this. So if your function is something like this, so it has Dr. Glech, if I am wrong, I'm not. So
it's a little bit more intricate than that. I mean, you can have a slightly,
Yeah.
the common function used to show the difference between, well, Chevy uniform is this Runge function. So it looks like basically like a normal distribution. So it's nice and smooth. It's
Yeah.
1 over 1 plus x squared, I think. Essentially what happens with that function is if you look at the error polynomial that you get for doing univariate interpolation versus Chebyshev, for that particular case, you can show that all of the error is concentrated at the extreme of the region, and so the error polynomial oscillates wildly. And so you get these really nasty effects. And if you sort of decide to optimize it, you discover that the Chebyshev polynomials are much better there. But that doesn't say anything about Chebyshev versus Taylor.
yeah, I mean, for the application I've seen, the Chebyshev polynomials are giving better approximation than the Taylor.
But I mean, Chebyshev are
But it depends. Sorry, it depends on the application you're using, like in the function.
You're constructing a Chebyshev interpolant of the function on the interval, whatever, to 1 or 1 to.
From let's say theta 1 to 1.
Okay.
Yeah.
So then it's just going to have to do with how I suspect it's not anything. I mean, I think classically, I think Taylor's is pretty slow at these log functions. And so, I mean, you're not really using that many terms in your Taylor series. And I think the denominator there is 1 over m, like it's 1 over k. So with 20 terms.
Like the Taylor series needs more summands than the number of Chebyshev polynomials that you are summing to get a better approximation.
I mean, there are faster converging series too. You could try.
Yeah, I know. I would just try this one.
Yeah.
Like the theory is more complicated than like implementing them. So yeah. Any other question? Okay, thank you.